Hello, welcome to video number 49. This is
Yes.
Lewis and Miller here. This is a very important video. We're going to go to the answers to the review worksheet for the quiz. Also, the write-up for the pasta experiment, that's review also. So the questions on there, you should be very familiar with how to answer.
Yeah.
Okay.
Okay. Let's get right into it. Okay. So we have some Kepler data.
Cool.
One of our favorite astronomers. All right. So we have our computer printout, so we don't need to do any crazy calculations. All right. And we want to do what's the equation for the least squares line? Pick a planet. The time for a planet to revolve around the sun. Excuse me. All right. Given the distance the planet is from the sun.
So the explanatory variable is
so we'll put revolve.
That's the response.
Right. Oh yeah.
variable.
The explanatory variable would be the distance. I'm sorry.
Yeah. So trying to explain
I was writing the equation.
It'd be like how long a year is for each of these planets, right? So
Yes.
a year is one
Right.
revolution around the sun. So this is a prediction of how many days would be in the year if you're on these planets based on the distance from the sun.
Right.
Okay. Amazing. Kepler was genius.
Yeah.
All right. Okay. Well, we have to look in the coefficient column. So
Right.
just a reminder, because it's been a while. Could you circle the column we're going to use?
Right here.
Okay, so the one that goes with constant, that's the y-intercept.
Yep. So negative 5,826.
Then the explanatory or x variables, distance. So the number that goes with the variable distance is the slope.
Right. Times our distance.
Wow. I just realized I don't have my calculator ready.
Remember,
but we didn't need it.
You can put y and x, but you probably should tell us what y and x mean then.
Yeah, that's what it means to define the variables. So it didn't say it this time, but sometimes on the quiz, on an AP test, it says define your variables. So this is a way of defining.
Right.
Okay, find the value of r.
Okay, well, they gave us r squared was 95.6%.
So this reminds me of something some people did on the last quiz.
Yeah, we take the square root of that, and what do we get?
Well, you want to take the square root of
0.956.
Correct. So the square root of 0.956. I just took the square root of I. Sorry, don't want to do that. 956 equals 0.977.
Right, 0.97.
Now, Mr. Lewis, there's another decision we have to make.
What would that be?
Is it positive or negative?
Oh, well, I'm going to think this is positive. The reason for that is our slope is positive, so I know my line is going up.
True. Very good point. I was thinking about the planets. The further you are, the bigger the orbit,
Yes.
the longer it takes to go around. So the bigger the distance, the bigger the time for one revolution.
That would also work.
Okay, either way.
Either way.
Now, just a little point. If you had taken the square root of r squared as it is, like I said, some people kind of did this. I'm not going to mention any names. They got r equals 9.77. A huge red flag. On the quiz, it was a different value. But they wrote things like r equals 18, r equals something like that. Some red flag should go off. R is in between negative 1 and 1.
Right.
So if you get a value that's not in between negative 1 and 1, a little voice of Mr. Lewis or Mr. Miller should be in the back of your head saying, something's bad, something's bogus.
Did something wrong.
Okay, forward.
Okay. So what is the slope? Well, we already kind of figured that out with our least squares line. Our
About
slope
15.
was 15.027. And include units. So that is...
The y units were days, because
Right.
it's how many days to revolve around the sun,
So days
per
distance.
and we
This
got to
is distance, so I'm probably
Yeah,
miles.
you got to flip. We got to go back.
All right, hang on.
It was in millions of kilometers. So it is days per million kilometers.
15.027 days
Per million kilometers.
millions of kilometers.
Okay, so what it tells me is for every additional million kilometers, that's quite a bit of distance.
Yes.
The days of the year increase by 15.
Right. So that would be the interpreting part.
Yeah. So on average,
for every 1 million kilometers,
that's the 1 unit in x, right?
right? The, I guess, revolution
Time, I guess.
around the, yeah, revolution, I should probably say time, yeah. Around the sun goes up or increases. Man, I can't write with this pen today. Okay. Increases 15 days.
All right. I hope they're listening, not reading.
Yeah. This is more of a more radio
Yeah.
when you're writing with the pen. All right. So again, on average, for every 1 million kilometers increase in distance from the sun, the time around the sun would increase by 15 days.
Gotcha. Now,
All right.
if the distance of a planet from the sun were changed by 4 million kilometers, that's a change in x 4, just 4, right?
Right.
Because our units are million kilometers.
Mm-hmm.
What would we expect the change in time for one revolution about the sun to be? Well, if this is not about standard deviations. You
Right.
see standard deviations there anywhere?
I don't.
So we just multiply the slope. We said it goes up 15 days roughly for every million kilometers.
Right.
So if it was 4 million kilometers, it'd be 15.027 times 4, which is 60.1. So remember, the slope is the rate of change. So if it's just about x changing by a certain amount of units, we use the slope to figure out the change in y that we would expect.
Mm-hmm.
So on average. Now, if the change is in standard deviations, that's different, which is the next problem. Okay, we did actually E. F. The distance of a planet to the...
We'll just
yeah.
do it again.
That's all right. If the distance of a planet to the sun is 2.5 standard deviations from the mean. So here the change in the x variable is given in standard deviations.
Mm-hmm.
The y variable is going to change by 2.5 times r. So 2.5 r standard deviations. Which would equal, and we'll explain this in a minute, why. We'll remind you why.
Okay.
Which would equal 2.5 times, r was 0.977, I think?
Yes.
2.44 standard deviations. So when the change is given in standard deviations,
Mm-hmm.
you multiply the change in x by r to get the change in y.
Right.
This is why it's called regression, because unless it's a perfect line, the y value will be always fewer standard deviations than the x value.
Right, because if you remember, it was r times the standard deviation of y over the standard deviation of x. That's how we got our slope.
Yeah, so multiply that by 2.5 r. I mean 2.5 sx. So to the right, times. That's the slope. If we multiply it by 2.5 standard deviations in x, the standard deviation in x can cancel. And we're left with r times 2.5 times sy. I don't know if you could write that there, but r times 2.5 times sy, which means 2.5 are standard deviations in y.
Mm-hmm.
Okay, so when it's just units, use the slope. But if it's a change in standard deviations, like 2.5 above the mean or something like that, multiply by r.
Exactly.
Okay. Is the y-intercept of the regression line meaningful in this problem, Mr. Lewis? What is the y-intercept?
It's a negative 5 All right, we're gonna work through the last problem. There's a technical glitch, so we're gonna work through H, I, and J, most likely, together. So here we have interpret the value of r squared in this context. So if you did that, you should have had 95.6% of the variation in days around the sun can be explained by the distance from the sun. All right, so that's a variation in y explained by x. All right. In I, here we have our residual plot. Remember, this is our 0 line right here. Okay, and so does the plot indicate that a line is appropriate? Well, the answer to that would be no, because there's this nice V shape right here. Okay, so the big no there. All right, even though it was 95.6% accounted for, still, or linearly, we don't want to do that. That would be more of a either exponential function or log function going through that one. All right, and then the last one. Number 9. I guess it wasn't J, it was 9. Okay, the labeled points below, which ones are influential? Okay, well, C is pretty obvious that it's not, because C is in the line. Okay, so then it's the question of A, B, or D. Now, I'm going to warn you right now, Mr. Miller and I really don't like how this question was worded, and on your quiz it'll be a lot clearer, okay, when we go through it. So when it turns to influential, well, D is a high residual point, okay? So it's going to change our r squared. So here we'll just go through each one. So here I have A, B, and D. Okay, so D, high residual, low leverage. Okay, it'll decrease our r squared, and our slope will be the same. So slope, same. Okay. All right, and A actually strengthens our data. Okay, so this is a high leverage, leverage, low, why am I not being able to write low? Low, let's just ignore this. Low residual, okay, it is going to increase our r squared, and then it may slightly decrease our slope. Looks like it's about the same as the slope though. Okay, and then in B is high leverage, okay, and it's going to increase our slope, because this is a negative slope, by changing our line, it's actually going to tilt our line more towards the positive arrow, so that's going to increase our slope. It's going to be less negative, and then we are going to decrease our r squared. Okay, this will be a lot clearer on your quiz. So, hope everyone